We now have the ability to propagate orbits forward and backwards in time for any orbit type. But the annoyance here is that we now have to keep track of a bunch of different variables. We have to check whether our orbit is closed or open, whether it's elliptical or parabolic or hyperbolic. We have to evaluate different anomaly variables. We have to evaluate a parabolic anomaly or a hyperbolic anomaly or an eccentric anomaly. And so there's just a lot of bookkeeping and overhead. What if instead of keeping track of different auxiliary variables, we could define a single variable that will just work for all orbit types? It turns out that we can, and we do this via something known as the Sundman transformation, which is named after Carl Sundman, who was a Finnish mathematician in the 19th century and early 20th century, who contributed greatly to the study of the three-body problem, as well as to numerical methods for astrodynamics. We are going to use a derivation first presented by Batten in his book, and it goes as follows. We start with the specific energy. The specific energy is the velocity squared over 2 minus gravitational parameter over r, and is equal to negative the gravitational parameter over twice the semi-major axis for all orbit types. We further rewrite this as, recall that we derived this form when defining the effective potential. And so we can solve this for r dot squared and find r dot squared is equal to 2 mu over r minus h squared over r squared minus mu over a. Substituting in the definition of the semi-parameter as a function of the specific angular momentum and the gravitational parameter, we can rewrite this as, and what we're going to do is define our universal variable, not in terms of itself, but implicitly in terms of its derivative. So we will define chi, our universal variable, such that its derivative, chi dot, in time, is equal to the square root of mu divided by r. What this means is that chi dot squared is mu over r squared, and r dot over chi dot squared is the same as dr d chi squared. And dr d chi squared by this and this must be, and this whole expression simplifies to, so dr d chi squared is 2r minus the semi-parameter minus r squared over a. Separating out the variables, taking the square root, we find d chi is equal to dr divided by the square root of 2r minus l minus r squared over a. If we assume that a is greater than 0, and we're not going to hold on to this assumption forever, this is just for now, assuming that a is greater than 0, we integrate both sides, and we get that chi plus c naught, which is a constant of integration, is equal to negative the square root of the semi-major axis times the arcsine of this argument. Since we've assumed that a is greater than 0 for the moment, this means that we are dealing with a closed orbit, and so eccentricity is less than 1. It also means that we can substitute for the semi-parameter as L equal to A times 1 minus E squared. And that means that eccentricity is the square root of 1 minus L over A, which means that our integrated expression now looks like chi plus the constant of integration C naught is equal to the square root of A times the arcsine of R over A minus 1 divided by E. We invert this to solve for R, and we find that R is equal to the semi-major axis times quantity 1 plus eccentricity times sine of chi plus C naught over root A. And this is going to be important to us later, so we're going to hold on to this expression. We're going to tag it with a star because we'll be coming back to it. Recall that we started off by defining chi dot as root mu over R, which means that we can now write d chi dt is equal to the square root of mu divided by this new form of R, which is a function of chi and C naught. Once again, separation of variables, we pull this denominator over to the left-hand side, pull the dt over to the right-hand side, and we integrate, and we find in this case, we have performed a definite integral between times t naught and t. And so on the left-hand side, we will have a times the quantity chi minus square root of a times e times cosine of chi plus c naught over root a, evaluated between chi at t naught and chi of t. And we're going to assume that chi at t naught is equal to 0. And on the right-hand side, where we just had root mu dt, we have root mu times t minus t naught. And we will call this, as we have been, delta t. So we now have a relationship between the change in time and a function of chi at some time t, but we still have this constant of integration c naught floating around, which we need to get rid of in order to actually apply this. We're going to do this in a couple of steps. First, recall the trigonometric addition formulas. So cosine of alpha plus beta is cosine alpha, cosine beta minus sine alpha, sine beta. If we apply this to this expression here, what we will get is so we have taken this summation where each term is scaled by root alpha. We've applied the angle summation formula to get this form, and we've applied that chi at time t naught is equal to 0. And so these are the only terms that are left. This is another important expression that we're going to want to come back to. So we're going to give it a little text dagger. And now we're going to briefly return to our start expression from earlier, this r expression over here. And we will use this to write r divided by a minus 1 is equal to e times the sine of chi plus c naught over the square root of a. If we evaluate this at a time t naught, then we find r naught over a minus 1 is equal to e times the sine of chi naught, which we're setting to 0, plus c naught over the square root of a. If we differentiate the start expression, we get, that is, the derivative of r is ae over root a, derivative of chi, cosine of chi plus c naught root a. Remember that c naught is a constant of integration, and so it has a 0 derivative. And as always, we have chi dot defined as root mu over r. Putting this together, we have r times r dot divided by the square root of quantity mu a is equal to e times the cosine of chi plus c naught divided by the square root of a. Remember a result from the F and G series. We found that r dotted into v was the same as r dot. And so we can replace this numerator here. And for example, at an initial time t naught, we can write, whereas before we're assuming that chi at t naught is 0. We can now substitute this back into the dagger expression, and altogether we find that is root mu delta t is equal to the semi-major axis times the quantity chi minus root a times cosine chi over root a, r dot naught dotted into v dot naught over the square root of mu a minus sine of chi over root a times quantity r naught over a minus 1 minus r naught dotted into v naught over root mu a. We're almost done. We just have one more substitution to make. We go back to our start expression here, and we apply the angle summation formula to the sine term here in order to write where we have used the relationship sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Applying our previous result relating r naught, v naught, and c naught, we can change this to that is r is equal to the semi-major axis times 1 plus sine of chi over root a times r naught dotted into v naught over the square root of mu a plus cosine of chi over root a times r naught over a minus 1. So we have now effectively eliminated the c naught variable from our equations, and we have an expression for r at a time t as a function of chi at that same time t and the initial conditions of the system. And this provides a summary of everything that we have just done. Okay, this is great and all, but we still haven't actually provided ourselves with a method for finding chi, because our initial definition was in terms of chi dot. So what do we do to get chi? Well, it turns out that we need to define another auxiliary variable. And we define psi to be chi squared over a, which means that the semi-major axis can be written as chi squared over this new variable, psi. What does this give us? Well, this allows us to rewrite our time and orbital radius equations as so root mu delta t is chi cubed times the quantity root psi minus sine of root psi divided by the square root of psi cubed plus r naught dotted into v naught over the square root of mu times chi squared times quantity 1 minus cosine of root psi divided by psi plus r naught magnitude times chi times sine of root psi divided by root psi. And similarly for the orbital radius, r is equal to chi squared times quantity 1 minus cosine of root psi over psi plus r dot dotted into v naught over the square root of mu times chi times quantity 1 minus psi times root psi minus sine of root psi over root psi cubed plus r naught times quantity 1 minus psi times 1 minus cosine root psi over psi. What we're going to do now, following Batten's method, is to define two new coefficients. C2 will be defined as 1 minus the cosine of root psi divided by psi. And right now we're dealing with a case where psi is greater than 0 because we started with the case of positive a, which makes this quantity positive. And we will define C3 as root psi minus psi root psi divided by psi cubed square root, which are the expressions that appear very often in these two equations that we just wrote down. So this allows us to simplify this horrible mess quite a bit. And what we get is root mu delta t is equal to chi cubed C3 plus r naught dotted into v naught over root mu times chi squared C2 plus r naught chi quantity 1 minus psi C3. And r is equal to chi squared C2 plus r naught dotted into v naught divided by the square root of mu times chi times 1 minus psi C3 plus r naught 1 minus psi C2. Recalling that in the closed orbit case, the mean motion n is equal to the square root of mu over a cubed, we can find that the square root of mu is equal to n times root a quantity cubed. And therefore, this first expression can be written as n delta t is equal to C3 times chi over root a quantity cubed plus C2 times r naught dotted into v naught over root mu a times chi over root a quantity squared plus r naught over a times chi over root a times 1 minus psi C3. If we instead considered the case where psi was negative, this is the open orbit case, then we would get in very, very similar looking expressions, but we would define C2 via the hyperbolic functions, like so. You can get to this basic result by going all the way back to the beginning of our derivation and setting a to be less than 0, and then chugging through the rest of it, and you'll end up with exactly the same forms. So at the end of the day, we now have a unified set of expressions with only a single check on whether one variable is positive or negative. And they allow us to write the orbital radius at any time as a function of chi, and the propagation, n delta t, as a function of chi and the initial conditions.